All right. So when I think about logs, I really look at problem 7 or problem 8 to think about logs as our entry point here. Um, what I had you guys do over and over again, what I taught you guys about over and over again was the idea that a log is a question. When you read that, one, there's how do you say it, log base 2 of 32, but then what does it mean? I kept asking you, what does this mean? When you filled out those like tables, and you kept writing it over and over again, what does this mean? What does this mean? A log is a question. You say log base 2 of 32, it's asking you something. What's the question that's being asked there when we say log base 2 of 32? What's this question? You remember? Okay. That's something different. That is a thing. That's not what I'm asking. That's called the change of base property. That's something else. Yeah. Of 32. What does that mean? What's the question that's being asked then? Addison, Kyla, Jarrett, Sophia, Theon, Jude. Another question? Two to the what is 32? That's the question. 2 to the what power is 32? That's what that means. That's the math that was tried to, that's the math that people were trying to figure out when logs were created. Okay? Logs were created to answer this question. So 2 to the what power equals 32. This is something we should be able to figure out. 2 to the second? No. 2 to the third? 2 to the fourth? 2 to the fifth? Yeah. 5 twos, right? 2, 2. Right? 2 to the fifth is 32. So the answer here would be 5. Okay. So what does a log mean? And then sometimes we can just figure them out. Okay. Sometimes they're available for us. So then looking at number 8, what's number 8 asking us? It says log base 3 of 1/9. What's that asking? 3 to the what power equals 1/9. Right, Mason? Okay. So how do we figure that out? Right. Well, 3 to the what is 1/9. We should be able to figure this out. How do we get fractions? From an exponent, how do we get a fraction?
Negative.
Okay, so we need a negative, yep. And then from 3 to 9 is the 2, right? So 3 squared is 9, so 3 to the negative 2 is 1/9. Okay, so recognizing how do I get a fraction? I need a negative. How do I go from 3 to 9? I need a 2. 3 squared is 9. So 3 to the negative 2. So log base 3 of 1/9 equals negative 2 because 3 to the negative 2 is 1/9. Okay. But again, this really is the important part here is what's the question, right? And so as we go back and we look at number 1, number 2, like when it's saying rewrite the log as into exponential form, how do we take that log base 4 of 16 equals 2 and rewrite it as an exponential equation? For me, again, it comes down to like covering up that right side and saying, well, what's this asking me? All right, what does log base 4 of 16 mean? Say, well, that means 4 to the what 16? Well, it's 4 to the 2 is 16. So as an exponential equation, it's 4 to the second is 16. So the answer is there for us. And that's kind of like a proof of concept type problem. Oh yeah, that does work. 4 squared is 16. And then we look at an actual equation on number 2 and say, well, how would I rewrite this? I'm not asking you guys to solve number 2, but just how would you, basically what's the first step? Okay. So when we say log base 3 of x equals 4, how do we rewrite that? And what I'd ask you guys to think about is what's that really asking you? You cover up that right side and say, what's that asking me? What's the question there? Sam, what's the question there on 2? Four's not there. Log base 3 of x. What's that mean? What does it mean? What's the question you're being asked? Log base 2 of 32 means 2 to the what is 32. So what does log base 3 of x mean? Two to the what is 32. 2 to the what is 32. How would you read that as a question? 2 to the what is 32. Three to the what is x. Okay, so 3 to the what power is x? Well, it's 3 to the 4th power is x. Okay, so now we bring that in. Once we know what the question is, then we can answer the question. Right? So the question is 3 to the what power is x? Well, it's 3 to the 4th power is x. And so there we've written the equation, but in a way that x is now isolated. Right? Look where x was. It was trapped inside of the logarithm. We couldn't figure out what x was, but now x is isolated, and if we wanted to, we got one more step, and we know what x is equal to. Okay? So how do you take a logarithmic equation, rewrite it so it's solvable, or now solved, really, and rewrite it as an exponential? Focus on that question. Okay? 4 and 5 and 6 are just backwards of 1 and 2 and 3. Okay? Here's the exponential form. Get it back into the logarithm. So it's basically, how do I take this and rewrite it here? Right? So where did the numbers come from? Where did this 4 come from? Where was it before? Okay, it was down there at the log base. So that 3 is going to be my log base. So when I'm done with this, I should have log base something of something equals something. Okay, so log base something of something equals something. So the 4 came from the base, so the 3 is going to be my base. A logarithm is an exponent. That was one of the first things I told you guys about logarithms. A logarithm is an exponent. So the exponent is the answer to the logarithm. Is in math means equals. A logarithm equals an exponent. And then the last thing we have a space for is the 81, and so it's got to go in the only space we have. Right? So log base 3 of 81 equals 4. Again, that's not a real problem because there's no variables there. You look at something like number 5, where there's a variable. Now it's actually like, okay, how do I figure this out? Good, Jarrett. So again, we're going to end up with, log base something of something equals something, right? We got to go and fill in those holes. So the base of the logarithm comes from the base of the power. I'm going to put a 10 there. The logarithm is an exponent. So the exponent goes to the other side. And left with that kind of last thing that we have there. The 1,000 is going to go inside the what's called the argument. The thing you're logging is the argument. So that'd be log base 10 of 1,000 equals 3. Except for we don't say log base 10. What's up, Caleb? Yeah, we don't say log base 10. We just say log. That's the button you guys have on your calculator. Right? That's the appropriate way to write that. Log base 10 is log. That's the common log, so we don't write log base 10. So again, remembering there is a 10 down there. We think about it. We just don't write it. So, okay. Now I ask you guys to try number 6 on your own. Okay. Real quick blast at remembering some stuff about logs, and we'll do some pretty simple logarithmic equations solving down here at the bottom. Kaylin was asking earlier about the change of base formula. We thought that would just be too much to have you guys try to remember. So none of the problems you guys will solve will require you to use the change of base formula, which is the thing that allows us to find the answers to logarithms we don't know. Right? We were able to figure out log base 2 of 32. We were able to figure that out. We were able to figure out log base 3 of 1/9. There's a whole bunch more that we couldn't figure out, like log base 2 of 10. That's not something we should just know. So the change of base formula allowed us to do that. You guys don't have to worry about that, though. So when you're looking at a problem like 9, that's an exponential equation. Look where the x is. It's stuck up in the exponent. How do I get that x out of that exponent spot? That's what happened. I'd write a 3 there. I'm going to write a 3 there. What was I doing? Give me an x. That's what we did there, right? We got the x out of that exponent spot by turning it into a logarithmic equation, right? We look at number 10. The x is inside of the log. That's what number 2 is like. Where we got how do we get that x out of the log? We turn it into an exponential equation. So just noticing what form it's in, then we're just gonna say, okay, I want to have to transform it. Here's the form it's in. I'm gonna rewrite it into this other form. I'll be back in just a second. Okay, so we have an exponential equation, number 9. Let's rewrite it as a log. Again, how I always talk to myself about this, I know that it's going to turn into a log. So I say, well, just kind of set up that form for myself. Then I go back and I focus on the pieces of it. Right? So I need the base of my log. That's going to be the base of my power. And there's that 10 we were just talking about. So I know there's a 10 there. I'm not going to write it this time. Okay? And then the exponent is the next thing I worry about. So the exponent is the answer. A log is an exponent, so that's going to go over there. And then the 533 just fills in the only other space I got. Kind of a process of elimination in your business. Okay, so log of 533 is equal to 2x. Well, we're a lot closer with knowing what x is. We're just not quite there, right? But we know how to get rid of a 2. That's easy peasy. So let's get rid of that 2. So x equals the log of 533 divided by 2. So there's our exact answer. That's what we're going to type into our calculator. And as silly as this may seem, you guys should all get your calculators and find your log button again. It's been a while since you've hit the log button on your calculator, so that on whatever day, this Thursday, you're doing this, you're not scrambling around trying to find your log button again. Okay, where's your log button? Make sure you close that parenthesis after the 533. Okay, just get used to doing that calculation again just a couple times. Get that muscle memory back. Round to the nearest 1,000 for either 3 places. So what's the log of 533 divided by 2? One point what? Oh, here's that. Yeah. Need 3 spaces. So 1.363. Okay. I'm not asking you guys to check this, but you certainly can check any of these problems really quickly. Say, well, what is 10 to the 2 times 1.363? Just make sure that it's close to 533. It's really fast. Okay. So there's 10 to the 2 times 1.363, 532. All right. That is right. So it's really quick. You check it for yourself. Everything's all good. Okay. So there's solving an exponential equation using a logarithm. And then here's solving a logarithmic equation using an exponential. Okay? So now we're trying to write some power of something. So we go back and we look and say, well, the base of my power is going to come from the base of my log. That's what's going to go here. A log is an exponent. So the exponent comes from the is side, the 3. And then, oops. Okay, equals something, and that's just what's left. So the part that's the argument is kicked over here. So we know that's log base 10. 10, and then it's 10 to the 3rd equals the 25x plus 50. Now in here we know what 10 to the 3rd is. 10 to the 3rd, or we can figure it out very quickly. 10 to the 3rd is 1,000. And once we have that, that's a basic level equation that you guys should be able to finish solving, no problem. Okay. But see how quickly we can go from something that looks really tricky to something that's actually really simple to solve. Just using that idea of transformation. One form of the equation to another makes it a lot simpler. Okay? Jordan, would you like to do number 11 or number 14? Okay. What's different between 11 and 9? Okay. So what should we do with that decimal? No, not yet. We want, in order for us to do the problem, it needs to look like 9. Like 9 is ready to go, but 11 looks a little different. So we need to deal with that difference first. There you go. So that, yeah, 0.25 can't be there. Again, when you're thinking about solving, it's thinking about SADMEP, and a logarithm happens at the exponential level of math. And so anything that's outside of that needs to be done first. So you add that 0.25 to both sides first. So 10 to the x equals 40.25. And now we can turn that into a logarithm. So log base something of something equals something. What's our log base going to be? Okay. Log base 10, so I'm not going to write anything. Jordan, what's going to go over here? X, okay. That leaves that. Why did I write 40.25? 40.25. Okay, so log of 40.25 equals x. Well, log of 40.25 is something you should just type right in your calculator. No more solving to do. Right, so what is the log of 40.25? It's something you guys all should be doing. Typing that in. Get used to hitting that button again. What are you guys? Go. Again, you can just type that real quick in. 10 to the 1.605 minus 0.25, which gets me really close to 40. Really close to 40. Okay, so, looks good. Mason, do you want to do 12 or 13? So 12 and 13 are very similar in the way that there's something in front of both of them, right? There's something after both of them, okay? And so that's, again, that stuff needs to be getting got rid of, just in the same way here that the subtraction, the division, multiplication, addition stuff needs to happen before we can deal with the logarithm. So what's the first thing we should do? Okay, add 3 to both sides. And normally we did like scaffold a little bit for you guys. Like normally there would not be a multiplication dot here when you write that. When you say 2 times the log of x, it would just say 2 log of x. And so that's just something that we did to kind of help you guys see that there was multiplication there. If you guys go after your next math class next year, that won't be there. So just being aware that it is multiplication there. Just visually, sometimes it's hard to see that that's a 2 times, but because this log thing is so new. Okay, what's next thing, Mason? What's next?
You take the
okay, so we get rid of that offending 2 there. So log of x equals 3.5. And so then from there, it's, again, that idea that we want to turn this into a power. So we have some base to some power equals something, right? So what's going to be the base of our power?
10.
Okay, yep, 10. What's that going to be equal to? What's going to be our... Yep, there you go. So 10 goes here, the x goes there, and that leaves the 3.5. Yeah, right. So x is 10 to 3.5, which again, you just type that in your calculator. You're done. What'd you get on that one? It's crazy, like 10 to the first is 10, 10 to the second is 100, 10 to the third is 1,000, 10 to the 3.5 is 3,000. Longer. All right, so there's those. I'll leave the rest of the ones on the front there for you guys to look at on your own. The word problems, they really should be pretty darn straightforward. Again, there's no solving you guys will need to do here. They're just reading the problem, pulling the numbers out, plug them into the right formula. Just finding that correct formula is really the trickiest part, and then type in your calculator. So there's no solving to do. We did solve problems like this, but we decided to do the easier version of this for the final. Definitely one of the main things you guys got to watch out for as you're looking at any of these is that what's going on with these percents. Every one of them deals with a percent, and making sure that you're using that number correctly as you go to do the math. 6% is 0.06, and 3% is 0.03, and 1.5% is 0.015. So make sure you're turning those percents into the correct decimals. That's a very common mistake people make with these types of problems. Tori, is that you? All right, I'm just talking. Yeah, I'm back. And then from there, it's really just about which formula is which, right? Which formula do I use when? Usually what it is, it comes down to a keyword in the problem. This middle formula here is the compound interest formula. And so you're looking to talk about that. It's that's a business application, compound interest. And so as soon as you see that word compound that's here in number 16, like that tells you to use that formula. Okay. The formula on the left there is the exponential growth formula. The formula on the right there is the exponential decay formula. For growth, you're looking for increasing, growing, expanding. I don't know, like things that are implying getting bigger. So we see the word increasing here in number 15. It says, hey, use that formula. Okay. And exponential decay, decreasing, shrinking, declining. Okay. Words like that. As soon as you see something like that, it's telling you to use that formula. But once you've got, kind of parse that out, it's just plugging things in. Look at the first one there real quick. Y equals the A value. That's the starting amount. How much did we start with? You can see here on this problem that starting amount was the 400 bald eagles that were there. Okay. Times 1 plus our R value, which is the rate, the 6, so 0.06, to the T power. T stands for time, 7 years. And you're just typing that in your calculator. Okay. I think you end up getting like 601.45 or something like that. But we don't have 0.45 of an eagle. We don't have 0.45 of a person. You don't have 0.45 of an object. Okay, so you're using appropriate rounding, saying, okay, I have to round that because it's an object, it's a person, it's an animal. And then you just say something like about, around, approximately 601 eagles. So I kept talking to you guys about like using appropriate rounding. It's not always the same. It's what's appropriate for what I'm talking about. Because when you go to talk about money, money has decimals. We use 2 decimals when we talk about money. So it makes sense to have decimals there. If you're talking about eagles, you're talking about population of people, decimals don't make sense. So be appropriate. So label your answer. But I'll leave those other 2 for you guys to do. Okay? But they should be pretty darn straightforward. And the last thing is the graphs, and it's a little tricky because we're coming like way out of context here. But all we're asking you guys to do is look at the domain, look at the range, look for any asymptotes that there are. We have some logarithmic graphs there, we have some exponential graphs there, and then on the bottom there's 2 rational function graphs. Those all have asymptotes. That's, we're talking about all that. And the asymptote is that line that the graph gets closer and closer to, but never crosses. That's our kind of our working definition for that. But we've talked about domain and range quite a bit throughout the the whole year. Domain, range. So just starting there. I guess something else was asymptote. But domain is this. Our x's. What x values do we see? We should be thinking left to right. What's the leftist thing I see? What's the rightist thing I see? Definitely on that right end, we see that it's it's heading off to the right forever. Something's kind of weird going on here. Right about what looks like about -2, something's happening. The graph doesn't seem to want to get much past that -2. But then we see that that infinity on the right side, and infinity's always got a parenthesis. Well, that -2 is coming from our asymptote. We have this vertical asymptote here. How do we write the equation of the vertical lines? How do you write the equation of a vertical line? Yep, x equals something, right, Jarrett? Okay, so this would be x equals -2. Well, why is it -2? It's because of that. All right, what's that +2 doing to this graph? It's shifting it left 2. We've talked about transformations so many times. So seeing that +2, saying, oh, there's my left 2. Saying, okay, that's why the graph is going over to -2 rather than being at 0 where it's supposed to be. An asymptote is a line that the graph is never going to touch, so that's going to get a parenthesis here. Okay. None of these graphs, none of them will have brackets on their domains or ranges. These asymptotes force them to only have parentheses. So left to right, range is low to high, start low, then look high. As we look at that low side over here, it's kind of hard to tell, but it is decreasing very, very slowly. It is dropping very slowly, and it's going to keep dropping very slowly as it heads off to the right. Okay. So that is a negative infinity. And of course, the upside, we can see it shooting straight up. It's going to keep going up forever. Okay. So left to right, low to high. But we see where that -2 showed up a couple times because of this. Okay. It's not a coincidence that -2 pops up over and over again. It's because of that left shift. So. When we did exponentials and logarithmic functions, they were right after each other. We talked about this idea of that one was the inverse of the other. What that meant was that the x's and the y's just switch. So our ideas for the domain and the range, they just switch. So it's going to turn out we're going to see that the domain of this function down here is going to be all real numbers. And we can see that it goes left forever. It's going to go right forever. And so that part switches. And then some's going to switch with the asymptote as well. So as we look left to right, we see that left end pointing left forever. There's a negative infinity. See that right end, again, it's slanting right. Okay, we don't care that it's pointing down, we care that it's pointing right. It's going to keep going right forever. The range, so we start low, go high, start on that low end. We see definitely it's pointing down forever. Then as it gets close to -2, it seems like it's kind of flattening out. Okay, so it doesn't seem like it wants to get much above -2. In fact, it's never going to touch -2 because our asymptote is at -2. And this is a y line because it's horizontal. And that's coming from this. So there's a shift down to. That's why that range and the asymptote have both moved to -2 rather than where they were supposed to be was at 0. for the parent function. Okay. So I just asked you guys to try 19, 21, see if that's something you're able to do there on your own. And then the last little bit here was 22 or 23. Caleb, which one do I do? Okay. So these are the rational functions. These are the hyperbolas. These ones have two asymptotes, a vertical and a horizontal asymptote. Okay? And where we found those, you can see them kind of on the graph. Is one of them was right there, and then the other one was down here. So we can see with the x, there's no number. So that vertical asymptote is at 0. So x equals 0 because there's no number there is where the asymptote is. So if there had been a 5 there, then it would have been -5. If there had been a -2 there, then it would have been at +2. Because there's no number down there, it's at 0. And then the horizontal one is at -3. We have a vertical asymptote. Horizontal asymptote. Dang it. Now, domain and range was, I think this is the only time we ever saw anything like this. The domain and range is a little different for these because of that break. These were called discontinuous graphs. The domain, as we approach from that left side, it goes, and then it gets really close to 0, and it's like, hits the brakes. Then all of a sudden, on the other side of 0, it starts again. So this is the only time we ever saw this went from infinity to 0, or I can't write infinities today. Then we had this symbol, the union symbol, from 0 to infinity. It had that break in it. It says I'm going to get really close to 0, I'm going to stop, and then I'm going to hop on the other side of 0 and keep going. And that 0 is the same 0 that's right here. Okay? It's the same 0 that's right there. And the range does something similar. God dang it. Okay? So it starts at -infinity, gets really close to -3, hops over -3, and it keeps going. Again, that -3 came from this. Okay? They're directly connected. So, all right. Okay, 22. See how it feels. Okay. Enjoy your weekends. Be safe. Okay.